Welcome to the last video today. And in the last video today, in this lecture about reinforcement learning, we will look into applications of reinforcement learning in natural sciences. And I brought 3 examples in total. The first 2 are 2 different approaches for molecular design again. But I don't want to end the whole lecture with yet another example about molecules, even though this is something I really enjoy personally. I will also show some example in the end that's maybe a bit more philosophical, which is about, can we use reinforcement learning to learn to experiment at all, like to learn strategies to experiment and to find out certain rules. But let's start with the molecules. In this paper here, Deep Reinforcement Learning for de novo drug design, the authors define basically molecular design as a game. And the reward is the properties of the molecules, and those are only known at the very end, which is why reinforcement learning that plays a game and modifies molecules and in the end observes some results is a quite suitable method for this scenario. In this case, they're combining a lot of stuff, which I really like this paper, that we learned in this lecture here. So first of all, they use a generative model, see, for example, in lecture 11, to define the actions that should be taken. And then they use a machine learning model for the prediction of the properties, and that's something we learned in lecture 10. And then they basically train both networks independent from each other. So they train the generative model they pre-train it to be good in modifying molecules. They train the probability prediction molecule to be good in predicting the properties of molecules. And then once the models are pre-trained, they start with a reinforcement learning algorithm. And in this case, they use a policy gradient method using the reinforce algorithm. This was not discussed in the lecture, so you don't really need to understand how it works. But that's basically what they're doing. So they pre-train a generative and a discriminative model, and then they use reinforcement learning to actually start for molecules, using the generative model to modify the molecule, using the discriminative model to predict the rewards, and then using reinforcement learning to learn how to modify a certain molecule to maximize the reward. This is very similar here in this other paper that I would like to quickly discuss. In contrast to the previous paper, these authors here use deep Q learning in optimization of molecules via deep reinforcement learning. They have a finite set of actions, and these actions are basically defined based on chemical rules. So they don't use a generative model, they just define a set of rules that are allowed to do in each step. And then a neural network predicts the Q values given a certain state, meaning given a certain molecule and a certain action that is allowed. And then they are trained exactly with this previously presented deep Q learning algorithm. So they use the experience replay, they use double Q learning with the Q prime and Q network. In addition to that, they use also some multi-objective design. So they show how we can merge several target properties in a weighted way into one single target property. And then they use this deep Q learning approach to optimize molecular properties. So basically in each step, they get a certain state, a certain molecule here. They define all possible actions that you can do. For example, you can add some OH group here, you can add a oxygen here, and so on. And then they evaluate using a neural network all the Q values, and they train it using the deep Q learning algorithm presented before. So you can see, also in molecular design, which is a topic we talked about a lot in this lecture course, we can use reinforcement learning to ultimately reach our goals of finding or optimizing molecules and molecular properties. But as I said before, let's go to more fundamental applications. And here I found this very interesting paper on arXiv, where the authors were thinking about, can reinforcement learning learn to experiment? And they described 2 different scenarios, 2 toy problems, but this can be applied to many other problems. So in the first scenario, they have these blocks, these cubes here, and they want the reinforcement learning to find out what to do in order to solve the question, what is the heaviest cube? And in the second scenario, they have this set of objects, and the reinforcement learning algorithm should find out what to do with these objects to find out how many objects are connected. So it might be the case that, for example, the green and the yellow one are connected, or the red and the green one. And the goal is that the reinforcement learning algorithm learns strategies to manipulate these objects, these cubes or the objects here, in order to answer the question, what's the heaviest cube or how many are connected? And the interactions that are possible by the reinforcement learning algorithm are, in the first case, it can apply a force on a cube in y direction. So in each time step, it can apply a force on this cube, and so on, and it can observe the environment. And in the second scenario here, it can either apply a force on cubes, on single cubes in x or y direction. So x would be like lateral, y would be vertical here. Or, that's scenario 2.1, or in scenario 2.2, it can indirectly influence by moving a sphere in x or y direction. So there's an additional object here which can bounce into other objects, and then we just indirectly manipulate these objects and observe the result of the actions. And then in both scenarios, they use two different observation methods. They either used some high-level features, which are basically directly the position of all the objects, and they used very low-level observations, meaning pictures of the scene. And this is called features or pixels. So in one case, the machine learning models were trained with directly observing the features, so directly observing the position of each object. And in the other case, the low-level pixels, mainly just the pictures of the scenes, were presented to the algorithm. So let's look at the heaviest cube problem. What we see here is a lot. We see here three different scenarios. The blue one has a very small weight difference, so it's the hardest problem. The green one has a medium weight difference, and red has a large difference in weight, which means that's the easiest problem. And now we look at what is the success probability that the reinforcement learning algorithm predicts the correct answer. So it does experiments and predicts the correct answer as a function of the number of steps that we have trained. You can already see this is a quite large number, so we have 10 million, 20 million steps that we have to do, but then we get very, very high probabilities that the reinforcement learning algorithm learns to predict the correct outcome. This is for the feature input. The same holds true for the pixel input. So it can learn both on the high-level features and on the low-level representation in terms of pixels to do correct experiments and to find good outcomes, or to find good strategies to predict the correct outcome. What we see here is the episode length. So in order to do the correct outcome and the prediction, in the simplest problem with the large weight difference, the red distribution here leads to rather short episodes. So the reinforcement learning algorithm already tells its result after, let's say, 3 to 5 steps. Whereas when the weight difference is small, it tries to experiment much longer before it decides to predict an output. And as a counter experiment, the authors experimented with randomized runs. So instead of taking the action that the reinforcement learning algorithm wants to do, they show what happens if the actions are picked randomly, but for training of the reinforcement learning algorithm, the actual observations are predicted. So basically, the randomized trial is degrading the reinforcement learning algorithm or the agent to some passive observer of random actions. And then they compared the probability of success of the active agent compared to the passive agent. And you can see that for the different scenarios with feature inputs F or pixel inputs P and different weight differences of 10, 5, and 3 for large, medium, and small weight difference, the active agent is much, much better than the passive agent. The passive agent still learns from the random actions and the actual observations, and this is actually getting better if the episode length is getting longer because the weight difference is smaller, but the active reinforcement learning agent is getting much more accurate in in predicting, which means that it actually learned some very good experimentation strategies to do exactly those actions that give the agent the observations that the agent needs to do good predictions. Application number 2 was the questions how many objects are connected, and basically it's the same result here. So here we only look at scenario 2.2. So this is called the fist scenario, where basically we have this additional object, and this additional object can indirectly can be moved in X and Y direction to manipulate the actual objects. And both in the feature representation, where all the object positions are given as result or observations, or the pixel, it learns very quickly to predict the correct outcome. And I guess, again, the passive observer, which is the randomized thing here, leads to much, much lower results. They're better than random, which is the dashed line here, but they're not much better than random, and they're much, much worse compared to the active reinforcement learning agent. So we have here 4 different outcomes: the direct manipulation with the D, or the indirect with the F, and then the feature observation or the pixel observation, and all of those lead basically to very high success rates, whereas the randomized trials are by far not as good. With this, I'm at the end of today's lecture. As a summary, we were in the first video discussing reinforcement learning as some interactive cycle between actions that an agent can take and the environment that the agent can observe, states and rewards that the agent gets from the environment that lead, in this case, to this sequential decision-making process where the goal is to maximize the future reward. We were looking at a mathematical description in the second video today, where we defined things like the state value function, the Bellman optimality equation. We discussed a couple of algorithms like the Q-learning and the deep Q-learning algorithm to solve this Bellman optimality equation. And then in the last video just now, we looked into some applications for molecular design, but also a more fundamental reinforcement learning application where the reinforcement learning agent has to learn to experiment. It has to learn to find strategies, what to do with a certain environment to find out and answer questions about the environment. With this, I'm at the end of this lecture and more or less also at the end of the lecture course. As I said, in the next week, we will have a shorter video which is summarizing all the different topics that we discussed in this course. We will put them into a bit of context, and then we will have an extended question and answer session where you can ask all the questions that are remaining, all the questions that you might have for the exam. And I hope this will help you to be prepared well for our exam. I hope you will have fun in the remaining last exercise. I'm looking forward to the question and answer session this week, and I wish you a good rest of the week. So see you in the question and answer session, and thanks for your attention.